Welcome to our visual presentation. We are of 3 members, myself Sauntinson, Subadu Tamang and Tashwangan. So, we will be presenting on the topic links and the joints of a robot. This is the outline of our presentation. Before going to the links and the joints of a robot, first we will be talking on the robotic arms. So, what's a robotic arm? A robotic arm, which is usually a reprogrammable, is a type of mechanical arm which will function similar to human arm, and it's a system made of links and joints with multiple degrees of freedom, with a manipulator at the end to perform various tasks like gripping, picking and placing objects and etc. The parts of robotic arms. The basic skeleton of arm contains upper arm, lower arm and the end effector. The end effector is attached at the end of lower arm, which will perform tasks like gripping, placing and picking. Some of the applications of robot arms are medical robots, military robots, automobile industry, domestic robots, space and exploration industry. Now, what is link? Link is also called as arm, and these are the rigid structure connecting the joints. The ground or a base is also called the base link and considered as link 0. Therefore, the number of links will be from 0 to n-1, where n is represented by the number of joints. Here, if there is 4 number of joints, then there will be 3 number of links, and if there is 3 number of joints, then there will be 2 number of links. Some of the common types of the links are binary link, which is with 2 nodes, ternary link, which is with 3 nodes, and quaternary link, pentagonal link, hexagonal link, which is with 4, 5 and 6 nodes. Next one is joints. What is joint? Joint is also called as axis, and these are movable components of a robotic arm that result in relative motion between the adjacent links. And the numbering of joints start from 1 to n, where n is represented by the number of joints.
So I'll be talking on types of joint. Number 1, we have a prismatic joint. It is also called as a linear joint or a translation joint. In this type of joint, we have a motion between the link is linear along the axis of prismatic joint, and the input link and the output link is parallel in this type of joint, for which we have 1 degree of translation freedom along the prismatic joint. Number 2, we have revolve joint. It is also called as hinge joint because it allows the rotation along the axis, along the single axis, and it is also have 1 degree of rotational freedom about the revolve axis. Number 3, we have a helical joint. It is also called as screw joint. It is similar to the screw motion, which rotate freely but cannot be translated freely, restricting its translation motion, and also have a 1 degree of rotational freedom along the axis. Number 4, we have cylindrical joint. It is also similar to revolve joint in series with a prismatic joint, but it has 2 degrees of freedom, with one being a rotational and other being a translation along the axis. Number 5, we have spherical joint. It is also called as ball and socket joint. It has 3 revolve joints intersecting at a point called the pivot with a rotation in 3 directions, and it has 3 degrees of rotational freedom about the pivot point. And number 6, we have universal joint. They are also called as universal coupling or hook joint, and it has 2 hinges joining at a point at 90 degrees to each other with their axis inclined to each other. And in this type of joint we have 2 degrees of rotational freedom about the intersecting point. Now, degree of freedom. It is generally defined as the motion capabilities of a system. It is also the total number of independent motion a joint can be performed. In most manipulator containing rotational and linear joints only, the degree of freedom is usually the number of joints performing rotational and linear motion. In general, a free body in a space has 6 degrees of freedom, in which 3 translation degree of a body along the x, y, and z axis, and 3 is in rotational degree of freedom, that is called roll, pitch, and yaw. And as a note, any free object in 3D space, example hand, fingertips, a car or plane, etc., can have most of 6 degrees of freedom. So, for taking the human arm as an object, how many degrees of freedom are there in human arm? For this we have solution. A human arm has 7 degrees of freedom, of which 3 are in the shoulder, 1 in the elbow, and 3 in the wrist. And all these degree of freedom can be controlled. And this is the formula to calculate the degree of freedom of a robot, in which M stands for number of degree of freedom of a rigid body, M equals to 3 for planar mechanism and 6 for special mechanism, and N is the number of link in the mechanism, C subscript I is the number of constraint provided by the joint. And constraint on a joint, they are used to restrict the relative motion between the 2 components at a joint, resulting in the degree of freedom of a rigid body system. And the type of constraint, we have 2 types of constraint, that is planar constraint and special constraint. And the table given is used for understanding the constraint on a joint. Activity 2, we have how many degree of freedom are there for mechanical arm in the clawboard. For this we have a result. We have on a robot joint M equals to 3, N equals to 3, C is equals to 5, and I is equals to 1. As a result, we have a degree of freedom. Using the given formula, we got the result as 1.